ASO Group begins steel production by melting scrap in an electric arc furnace. The molten steel is then transferred to a ladle furnace for refining, where its chemical composition and temperature are precisely adjusted. After this, the steel undergoes vacuum degassing to remove impurities. The refined steel is cast into ingots, which are then reheated in furnaces. These ingots are forged using powerful hydraulic presses to achieve the desired shape and structure. The forged pieces are heat-treated in controlled conditions to improve mechanical properties. Finally, the bars are straightened, cut, and subjected to rigorous quality checks. Throughout the process, the material is carefully tracked to ensure consistency and quality. The process begins with loading heated steel billets into the forging line. A robot arm transfers each billet to the preforming press, which shapes it roughly. Next, the billet is moved to the 6,500-ton Sumitomo hot forging press, where it is forged into the crankshaft form with high precision. The forged crankshaft is then automatically transferred to a trimming press to remove excess material. After trimming, the crankshaft is moved to the punching process to create holes. Cooling follows, where parts are aligned and transferred by robots to a cooling conveyor. Finally, a visual inspection is performed to check shape accuracy and surface quality. The entire line operates automatically with synchronized robotic systems to ensure continuous and efficient production. The DB12500 CNC is designed for grinding extra-large crankshafts up to 12.5 meters. The crankshaft is first positioned precisely between two chucks. The machine's hardened ball screw system ensures accurate longitudinal movement. Grinding is performed smoothly thanks to the alloy cast iron structure. The process includes rough grinding of the main journals, followed by precise finishing passes. Nanomet technology quickly checks for unbalance during machining. The travel setup is rapid, with a fine feed of 5 mm per cycle, ensuring both efficiency and surface quality throughout the crankshaft. To join the open ends, a mag root weld is first applied to prevent burn-through. Then, submerged arc welding is performed in layers using a parallel welding system with 2 overlapping wires, effectively doubling the welding capacity. Forging, machining, welding, assembling, and testing large steel components for nuclear reactors with high precision and safety standards. The production of large bevel gears starts with CNC turning and grinding. Gear teeth are cut using advanced bevel gear cutting machines. After machining, the components undergo in-house heat treatment. Grinding follows to achieve high surface quality. Magnetic particle testing detects surface cracks, and grinding burn inspections ensure quality. Final inspection of each gear is performed directly at the factory. The 6-sided turn and mill complete machining of a stainless steel surgical hammer on the NTX 2500 involves turning, milling, drilling, and contouring operations. The process includes precise shaping of the hammerhead and handle, using synchronized spindles and multi-axis machining to achieve high accuracy in a single setup. The Trumpf TrueBend 7000 precisely bends small to medium-sized metal parts using high speed. The operator positions the metal sheet and selects the bending program. The machine automatically adjusts the tools using bend guard. With ACB angle measurement, the first bend is checked and corrections are applied. Then, the machine quickly produced high-quality parts with minimal manual adjustment. Hydraulic cylinder assembly process. The assembly process of a hydraulic cylinder begins with the preparation of all main components, including the grooved cylinder tube, hard chrome-plated rod, piston, seals, and end caps. First, the piston is precisely mounted onto the rod, followed by the installation of rod seals and piston seals. These sealing systems are designed to ensure long-term, leak-free performance. Next, the rod piston assembly is carefully inserted into the cylinder tube. After positioning, the end caps are mounted and fixed in place using high-strength screws. During assembly, special attention is given to alignment and cleanliness to avoid contamination and ensure reliable operation. Once the mechanical assembly is complete, the cylinder undergoes a final pressure and cyclic motion test. The system records all test data and can issue a performance certificate upon request. The automated rail manufacturing process. The rail production process begins with combined top and bottom blowing converters, followed by refining in ladle furnaces. The molten steel then undergoes RH vacuum treatment to ensure purity. Next, it is cast using a 6-strand continuous bloom caster. The solid blooms are rolled in a 7-stand universal rolling mill to form rail profiles. These are then processed through an online heat treatment and testing center to enhance mechanical properties and ensure quality. Finally, the rails are straightened using a complex straightening machine, then cut and drilled by a combined sawing and drilling machine, ready for shipment. Oxy-fuel cutting utilizes a high-temperature flame and pure oxygen to efficiently cut through 850 millimeters thick, mild steel. North Shore Steel uses a Davi 3-roll machine to bend thick steel plates into cylinders. After rolling, edges are aligned and tack welded. Final welding secures the seam. The piece is then checked and corrected for roundness, ensuring precision before moving to the next fabrication stage. The process begins when the 25 millimeters thick metal sheet is first positioned against the back gauge for accurate measurement. The operator adjusts the settings, then initiates the cut. The upper blade moves straight down, driven by the hydraulic system. As it descends, the blade shears through the sheet in one continuous motion. The cut is made along the full width of the material. After cutting, the metal piece falls or slides down onto the support area for collection. Bien Aluminium produces aluminum by melting raw materials in furnaces, casting them into ingots or billets, then cooling, cutting, and packaging them. The process includes alloying, granulation, and deoxidation stages, all performed with advanced technology and in accordance with international production standards. The D53 CNC machine uses Siemens PLC to perform radial and axial rolling. A heated ring blank is clamped, then progressively expanded and shaped by rolling, achieving precise outer diameter and height control from 350 to 8,000 millimeters and 60 to 800 millimeters respectively. The sailor releases the brake on the windlass, allowing the anchor to drop freely. As the anchor falls, the chain rapidly pays out. The descent is monitored to control speed and prevent tangling. Once the desired length is reached, the brake is applied to stop the chain. The 19 centimeters thick, nearly 50-ton gas pipeline project includes stem extension assembly, testing, sandblasting, painting, gear mounting, and special packing. After quality checks, the unit is picked up and transported by Cardo Air Freight, ensuring secure and efficient delivery to its destination. Slag from steelmaking is discharged from specialized rail cars onto the slag yard for cooling and further processing. At Liberty Steel Dalzell, scrap steel is melted in an electric arc furnace, refined in a ladle furnace, and cast into slabs. Slabs are reheated, descaled, and rolled in a reversing mill to precise dimensions. Plates are then cooled, cut, tested, and prepared for dispatch. At Saab's hot rolling mill in Bourlange, steel slabs are first reheated to high temperatures in a furnace. Once heated, the slabs enter the descaling unit, where high-pressure water jets remove mill scale from the surface. The clean slabs then pass through the roughing stand, where they are rolled into thinner transfer bars. These bars are then guided through looping tunnels to maintain proper tension and alignment. In the next stage, the bars enter the finishing mill, consisting of several rolling stands that progressively reduce the thickness and improve the surface quality. Finally, the hot rolled strips are cooled and coiled for further processing or delivery. At Isuzu, the forging process starts by cutting iron bars into appropriate lengths. These bars are then heated to around 1,200 degrees Celsius to make the material easier to deform. Once heated, the material is placed into a die and shaped with a 4,000-ton press. The first die gives the material a rough shape. Then, a second die is used to form the finer details. After forging, any excess material is removed. The forged part is cooled slowly to prevent deformation and ensure dimensional stability. This completes the forging stage. Afterward, the part undergoes machining and heat treatment to achieve the final specifications. Wax patterns are molded, ceramic coated, metal cast, cleaned, machined, and inspected to produce turbine blades and vanes. The Obervermutwerk 2 pump storage power plant began in May 2014, involving extensive underground engineering to minimize environmental impact. One of the main components is the 3 kilometers long Silvretta headrace tunnel, excavated using the drill and blast method through hard geological formations such as granite and gneiss. This tunnel channels water from the Silvretta reservoir to the powerhouse. A critical structure in the system is the pressure shaft, which descends at a 48-degree angle. Steel pipes used to line the shaft were produced by Bilfinger VAM in Wels, Upper Austria. The pipes, made from centimeter-thick steel plates, were rolled and bent into 4.5-meter diameter sections. Each segment was around 10.5 meters long and weighed about 45 tons. These were assembled in the cavern, welded together by specialized workers, and carefully lowered into the shaft using a 60-ton capacity winch. Due to the steep angle and heavy weight, the process required extreme precision and secure handling. The underground powerhouse cavern is located near the Vermont Reservoir. Measuring approximately 117 meters in length and 33 meters in height, it was excavated with the removal of about 115,000 cubic meters of rock. Inside this cavern, 2 machine sets were installed, each consisting of a pump and a Francis turbine. The equipment was supplied by Andritz Hydro and Voith and required complex assembly on site. Transportation of these massive components was performed using specialized vehicles and cranes capable of handling loads up to 180 tons. At the lower end of the pressure shaft, a Y-shaped pants pipe, Hosenrohr, was installed to split the water flow evenly between the 2 turbines. Given the extreme water pressure at this location, all components had to be especially robust and precisely engineered. Operation process. Obervermutwerk 2 operates as a reversible pumped storage facility with an installed capacity of 360 megawatts. During periods of low electricity demand, water is pumped from the lower Vermont Reservoir to the upper Silvretta Reservoir using surplus electrical energy. When electricity demand is high, the stored water is released back through the pressure shaft, driving the turbines to generate electricity. To handle pressure surges, the system includes a 292-meter-high vertical surge shaft, Crespa, which stabilizes pressure fluctuations and protects the infrastructure from hydraulic shocks. This ensures safe, long-term operation. All systems are monitored and controlled remotely from Ilwork VKW's control center in Vandens. The design enables rapid adjustments based on real-time energy demands, ensuring flexibility and efficiency in electricity production and storage. The Ramp Tech Plus system enables automated adjustment of mold inclination for staircase ramps with integrated landings. Upon setup, integrated tilt sensors determine the required step heights and landing angle, which are then adjusted via electric actuators. Shuttering elements are precisely positioned to define the casting geometry. Concrete is poured and compacted using high-frequency or pneumatic vibration systems. The fixed table, featuring a polished casting surface and integrated heating systems, ensures optimal curing and high-quality surface finish. Lateral shutters allow for the production of elements with variable dimensions and thicknesses. At Havells India's Alwar plant, the cable and wire manufacturing process begins with the procurement of high-purity 8mm copper rods. These are drawn down to 1.6mm wires and annealed to enhance electrical conductivity. The wires are then stranded into flexible conductors using high-speed machines. Insulation is applied via precision extrusion, monitored in real time by Sakura X-ray systems for accuracy. Depending on the product, further layers such as inner sheath, armoring, and outer sheath are added. Finished cables undergo strict quality tests before being coiled and automatically packaged. This process supports the production of advanced cable types, including flame retardant, fire survival, and solar cables. At Koffler, the motor rewinding and reassembly process begins with the random winding of multi-strand stator coils, followed by layer winding for the rotating field coils, and random winding for the rotating exciter rotor. The careful replacement of various laminated core sections in a 3,500 kilowatts generator. A laser-guided tool is used to precisely cut the grooves of the commutator on a large rotor, ensuring accurate slot alignment. The process continues with coil winding and insulation for both AC and DC armatures, involving various winding patterns and insulation techniques. The coils are then inserted and wedged into newly rewound stators, ensuring tight mechanical fit and optimal electrical performance. Each stage is performed with precision and is closely monitored to meet high standards of quality and reliability in electric motor and generator rebuilding. The process begins with electrodeposition of copper onto rotating titanium drums in an electrolyte solution, forming 8-micron copper foil. As copper deposits evenly on the smooth drum surface, it creates a double shiny finish. The foil is continuously peeled off, cleaned with water, guided by rollers, and dried under tension control to ensure uniformity and surface quality. Zanini Rank is a Brazilian company specializing in the production of high-performance speed reducers and gearboxes for various industries, including cement, mining, steel, sugar and ethanol, naval, and energy sectors. Established in 1976, the company has built a reputation for delivering reliable and efficient power transmission solutions. Their manufacturing process integrates advanced technology and precision engineering to ensure high-quality products. Utilizing state-of-the-art equipment like the Sorolus Vertical Machining Center, Zanini Rank achieves tight tolerances and consistent quality in their components. Embracing Industry 4.0, they have implemented Siemens Ops Center solutions to digitize their operations, enhancing efficiency and visibility across the production line Site Turn 0 Search 1. This digital transformation has led to significant improvements in productivity and customer satisfaction. The company's commitment to innovation and excellence positions them as a key player in the global industrial machinery market.